Hello and welcome to 11.3 Notes. So in Chapter 6, you learned that if two polygons are similar, then the ratio of their perimeters, or of any two corresponding lengths, is equal to the ratio of their corresponding side lengths. Okay, that was something we went over in Chapter 6. In other words, anything that is linear or in a straight line, or anything that's one-dimensional. For example, anything that could be measured in, say, feet, or inches, or yards, or meters, or centimeters. Anything like that, anything that can basically become a straight line, any length, or even a perimeter, right, which is just a series of straight lines. Anything like that, if you have two polygons that are similar, then the ratio of their corresponding side lengths will equal the ratio of their perimeters. It's a 1-to-1 ratio. But today's lesson is on the ratios of areas of similar figures. So if you have two similar polygons, then the ratio of their corresponding side lengths will be different than the ratio of the areas. Okay, again, I'm going to repeat that because that's key. That's the important thing here. If you have two similar figures, the ratio of their corresponding side lengths will be different, a different ratio than the ratio of their areas. Okay, and I'd like you to write this down now. You're responsible for this theorem. The areas of similar polygons. If two polygons are similar with the lengths of corresponding sides in the ratio of A to B, then the ratio of their areas is not A to B. It's not the same. It's different. It's A squared to B squared. And that's the key. That's extremely important that you know that it's different. If the ratio of their lengths is A to B, that does not equal the ratio of their areas. The ratio of their areas would be A squared to B squared. Okay, it would be different. So if you have a linear ratio of, say, A to B, then the ratio of their areas will be A squared to B squared. Okay, I cannot emphasize that enough. It's different. It's not in the same ratio. So please write this down. You'll be responsible for that theorem. And remember, you're in total control of this presentation. So if you'd like to pause it, fast forward it, rewind it, you're in total control, and use this presentation as you see fit. Okay? So if we have polygon 1 with a side length of A, and polygon 2 with a side length of B, and the two polygons are similar, okay, then we can calculate, right, that the side length of polygon 1, which is A, and the side length of polygon 2, which is B, are in a ratio of A to B. And so if they're in a ratio of A to B, then the area of polygon 1 divided by the area of polygon 2 is not A to B, it's A squared to B squared. Okay, so please write that down, get caught up, and of course you can pause this, but for the sake of this presentation I'm going to continue, and I'm going to demonstrate for you how that works out, why the ratio is A squared to B squared if the linear ratio is A to B. So let me change color here for a little bit. Okay, so please draw down these two triangles, rectangles, these two rectangles, and they are similar rectangles, and this one has a width of 3 and a length of 12, and the other one has a width of 4 and a length of 16. Okay, so let's talk about the ratio of side lengths. Okay, the ratio of their side lengths, it's in a ratio of 3 to 4, right? We have a ratio of 3 to 4. And so the ratio of their perimeters is also going to be the same. Again, that's something we covered in chapter 6. The ratio is also going to be 3 to 4. Let's see if that's true though. Let's work that out. Let's see if that actually works out. So the perimeter of this rectangle is 3 plus 12 plus 3 plus 12. This way, right? So you add up, right? Perimeter is the distance around a figure. So this would be the perimeter of this rectangle. And then the perimeter of this rectangle is going to be 4 plus 16 plus 4 plus 16 again. Okay? So that's where we get that from. And then you add them up and you get 30 divided by 40, which reduces to 3/4. So yes, the ratio of their perimeters is 3/4. Again, the same as the ratio of their side lengths, which we learned in chapter 6. But now we're going to talk about the ratio of areas, which is today's lesson. What's your prediction? What do you think the ratio of the areas will be? Again, you can pause this, write this down. You can pause this right now. But I'm going to continue. So what's the ratio of their areas? Well, let's calculate that. The ratio of this area is gotten by going 3 times 12, right? Area of a rectangle is length times width. So we have 3 times 12 to get the area of this rectangle. And then this one, area, is length times width again, which is 4 times 16 right here. Okay? So we have the two ratios. 3 times 12 is 36, which is the area of this. So the area of this rectangle is 36 square units, right? 3 times 12. And the area of this figure is 16 times 4, which is 64 square units. So we have the ratio of 36 to 64. And I want to divide by my magic number 1. Remember, dividing by 1, dividing any number by 1, you still keep that same number. But I'm going to reduce it. I'm going to reduce it by 4 over 4, right? 4 divided by 4 is 1. So I'm not changing the identity of this number. I'm just reducing it. And that comes out to be 9/16. 9/16. Okay? So the ratio of their areas, say if this is little a and this is big A, the ratio of their areas was not 3/4. Okay? It was not 3/4. It was 9/16. 9/16, which is the square, right? 3 squared over 4 squared. So we have, if we're going from the linear ratio to the area ratio, then you square it. So if you have the linear ratio is 3 squared, then the area ratio is going to be 3 squared over 4 squared, or 9/16. Again, that's very key. You cannot use the same linear ratio when you're talking about the areas of, when you're talking about the ratio of areas. Again, you cannot use the same ratio as the linear ratio when you're talking about area ratios. You have to square it. Okay? Okay, and we have 2 example problems to work with. Here's the first one, so please copy down this prompt. We have 2 triangles. This one has a length of 2 inches. This one has a length of 3 inches. And we know the area of the left triangle is 6 square inches. And the area of this triangle is what? What would be the area of this triangle if I know the area of the other triangle and I know the 2 ratios? And again, these are similar triangles. Okay, these problems can only be done with similar polygons. So they are similar triangles. And let's talk about the linear ratio first. The ratio of this triangle to this triangle is 2 to 3, 2 over 3. So the linear ratio is 2 to 3. So what then would be the ratio of their areas? The ratio of their areas is not 2 to 3. It's not 2 to 3 when you talk about the ratio of the areas. It's 2 squared over 3 squared. Remember, you need to square them. And that's going to be 4 over 9. So the area ratio is 4 to 9. So now we can use that ratio and set up a proportion using that area to find this area. Okay? So now we can set up a proportion after we know the ratio of their areas. But remember, first we have to square it. So if we have the area of the left-hand triangle over the area of the right-hand triangle, we know that's in a ratio of 4 to 9. That's where I get the 4 to 9 from. We just figured that out by squaring the linear ratio. And then we have that equals 6, because that's given, over this area. And for now, we'll just call it x. Okay? So that's where you get this proportion. So now we just solve this proportion by cross multiplying, and we get that 4x is equal to 9 times 6, which is 54. And then we divide both sides by 4 and get that x is equal to 13.5. So the area of the right-hand triangle is 13.5 square inches. Okay? And then our second and last problem, the area of this left-hand rectangle is 49 square feet, and the area of this rectangle is 16 square feet. So please copy down those prompts, write that down, and we also have that the perimeter of this rectangle is 42 feet, and we need to find out what is the perimeter of this smaller right-hand rectangle. Okay? So now actually we know the ratios of their areas. And the ratio of their areas is 49 to 16. But what is the ratio of their perimeters? So now this is sort of the opposite direction as problem 1. Problem 1, we went from linear to area ratios, right? Linear ratio to the area ratio. We squared that. Right? You square the linear ratio to get your area ratio. But now we're going from area to linear, so we need to square root it. Okay, we need to go the other way. We're going to take the square root. So the linear ratio is not 49 to 16, but rather the square root of 49 over the square root of 16, which is 7 over 4. So the linear ratio is 7 to 4. Now we can use that in our proportion to solve for the perimeter of the right-hand rectangle. Okay, so we have information for the left rectangle over information for the right rectangle, and we know that that's in a linear ratio of 7 to 4 because we took the square root of the area ratio, right? And so it's in a ratio of 7 to 4, and then we have that equals this perimeter, which is given, right, for the left-hand triangle, over this perimeter, which we need to find out for the right-hand triangle. So this is the proportion that we need to solve. Okay, again, we cross multiply, and we get, hold on here, cross multiply, and you get that 7x is equal to 42 times 4, or 7x is equal to 168, right? 42 times 4 is 168. And so dividing both sides by 7, you get that the perimeter of this rectangle is 24 feet. Okay? And again, as usual, if you have any questions or concerns, please feel free to contact me at your convenience. Ask me questions at any time you'd like, and it would be my pleasure to help you as best I can. Okay? Thank you. Bye-bye.